Okay. Hello,
Hello.
everyone, and welcome to
Hey,
another K6 Office Hours. This is a reminder to not talk about funny subjects just before hitting go live. I'm Nicole van der Hoeven, and today I'm coming to you live from Antwerp, Belgium, where I just did Eurostar. I also am joined by my two colleagues, one that you've already seen on the channel before, Leandro. Why don't you introduce yourself?
Hello, everyone. Leandro, also known as Señor Performo. Very happy to be back in person to this place. Last week, I think you saw us Vegas, baby, but now I'm home, baby. So it's very good to be back.
And we managed to convince, I think, one of the newest members, maybe not the newest member anymore, but one of the newest, I think, to the K6 team. Bro, or Roberto Santalla. Why don't you introduce yourself?
hey, nice, super happy to be here. So yeah, my full name is Roberto Santalla. I can go by Roy, shorter. Makes everybody's life easier. And yeah, I joined as a software engineer to the K6 team, and I'm working actually on the chaos side of things. Someday I think we will probably talk in more depth about the project I'm working on. It's still quite new, so it's not ready yet, but
Top
soon it will be.
secret.
Yeah.
Actually, it might not be ready, but we already have talked about it. We've had Pablo come on
Oh,
and talk about it. Come on, this is K6 where we
we
talk
will.
about things that are not fully fleshed out and the things that are fully fleshed out.
We just can't
Then we
shut
will
up.
talk about it again.
Yeah, so it's not a secret, sorry. We just had GrafanaCon 2023, and this is like a free virtual event, and it's already done, but if you go to this link, you can still catch up on what you've missed. There were actually some really some cool talks, including two by our K6 champions about K6. There was one by Jose Luis Latorre Millas. He talked about how Grafana K6 helps you break your APIs to make them stronger. And then John Hill, I think both of them have been on office hours. I think John Hill did one with Marie. He talked about automated performance modeling with NASA OpenMCT, Grafana Cloud, and K6. It's so awesome because these are like real use cases of K6 in the wild. So if you didn't catch it, then you should absolutely watch it in that link. Ro, why don't we talk about what you're doing here? Wait, when did you even come to K6?
Yeah, happy to elaborate. I joined K6 and Grafana, I think about a month and a half ago. So technically, the very end of April, I counted as just May. So I've been here for a month and a half.
Super
How,
fresh, super new.
Yeah.
how
How's the
did we
experience?
convince you?
Oh, that's a nice question. So I wanted to change a bit the kind of theme I work on. Actually, my previous work was more or less also in observability, making tools for developers, instrumentation, infra, all that. But I wanted to get to try out the more open source side of things. So I basically Pablo and Pavel convinced me by both selling to me the Disruptor project. I'm super. They got me super interested. I think it's a super interesting project, and also they told me that this will be a very open source focused role. So I was in for both of these things. And yeah, here I am. It was not hard to convince me.
I mean, it's
That's good
attractive,
to
right?
hear.
It's
Yeah,
interesting.
Yeah, definitely.
you made the right choice.
Yeah, I think so.
Yeah. So we actually, I think, for those who don't know, everyone who joins the K6 team goes through this thing called Week of Load Testing. I mean, we say load testing, but it doesn't always actually have to be load testing. The idea is that you have a week where you just play with whatever part of the K6 stack that you want to. Some people have focused on the accessibility part, some people on front end performance, others on back end, others like write a wrapper around K6. So you can do pretty much whatever you want to. And then the idea is at the end you present something to the team. And so this was my introduction to Ro, and he had this very awesome presentation that I actually missed the first time around, but I did go back and watch the recording. How was that experience for you, just using K6 for the first time?
Yeah, so I think it was pretty nice. Actually, it felt. I think the initiative is a very nice thing, right? Because as someone that very recently joined the team, I'm in a position where I'm not cursed by the knowledge, as one typically says. That I'm not biased by decisions that I've been either part of or that I have witnessed in like very very closely. So I think it's very nice to give this a nice opportunity to try out and give the feedback. And yeah, I think so far the experience was great. I was very happy with the tool, very happy with the documentation, especially with the documentation. Chef kiss, one chef kiss for the docs team. It's really great, and it's something I personally look a lot into when I I deciding if I want to use a tool. So it was great, good experience. Some things that of course didn't work at the first time. That yeah, you pretty much can't run away from that.
Like what? I'm curious.
Oh, like what?
Yeah, you got my
So
interest.
yeah, something that required me to play around a bit was, for example, using K6 Cloud when you run K6 from Docker, because you need to log in to K6 Cloud, and either to upload results or to have the cloud run the test, whatever you want. And when you log in into the cloud, this needs to store a token somewhere. But if you are just running Docker run, this token will be stored nowhere, or will be stored somewhere, and then we will be wiped out. So I need to mess a bit. But I don't know, it's something that anybody who's familiar with Docker can solve.
Details,
I think
but something that I think, hey, devs watching.
Yeah, I think they took note. So yeah, fair note. I haven't checked if it is fixed or documented or whatever, but I think they are aware.
Guess who didn't watch Rose week of load testing because they talked about that. Come on, Leandro.
We got you.
Yeah.
No. I'm just doing like an extra adding pressure so that
Oh,
hey,
sure.
this is public now. No, I watched it. I was very impressed by the
Okay.
week of load testing.
Well, why don't we get
Really good.
into some of your slides? Although I hope you don't interrupt. You don't mind if Leandro and I interrupt occasionally to be like, "Wait, what? What does that mean?"
No, not at all. By all
Kuber
means,
what?
like Kuber what? That would be a very interesting question to answer. Awesome. Yeah. So I can move on with the slides, but exactly as you said, just feel free to interrupt and yeah.
Yes,
by
I
all
will.
means. I'm counting on that. So I have preemptively titled this K6 and K8s or Kates. Doesn't matter how you pronounce it. It's everybody mostly knows it's short for Kubernetes or Kubernetes, or it's like a very nice word nobody knows how to pronounce. It's very funny. And yeah, these slides are going to be about me using K6, as Nicole explained during my first weeks in the team. And I thought it was going to be a nice idea to use K6 to figure out some details about and find some bottlenecks about yay. So before jumping into that, I got the compulsory about me slide. I'm compelled by international law to have a slide saying about me. Interpol will get you if you don't. I don't want to spend a lot of time on this. I'm a software engineer. I mainly code Go nowadays, but I also have some background in several languages: C, assembly, JavaScript, Python, Shell. Python not a lot. I'm not good at Python. Shell, YAML, and whatnot. And I really like infrastructure. I think you will notice this as we talk and I get into the juicy bits. But yeah, so I enjoy mixing both things, like development and infrastructure. So yeah, let's hop into the introduction and what is going to be the focus of my efforts, and that's the focus of what I'm going to tell you. And I titled this, okay, how many bytes can I speed through my front door? Which is, okay, in more technical terms, I have a home lab at home, some nodes, Kubernetes nodes, and I run some applications in there. Mostly they are like media servers, like Plex, Jellyfin, for whoever is familiar with those. And yeah, it's like small scale servers that friends and family services that friends and family can access. And this is like, you can see on the right, a bit of an overview of how this works. We have the internet, connects through a router, like mostly everyone nowadays. This routing is doing NAT, port forwarding, and then you have a switch, and the nodes are connected to this switch. So, and then I have a Kubernetes cluster that runs the services, and I will run into more detail about this later. But so yeah, the goal was to see, okay, what is preventing me from fully utilizing my the connection that my ISP provides to send things outside. Like if someone wants to get some media that they have stored, what will be preventing them from getting that media at the maximum speed possible? And
So I
yeah,
already have a question.
Yeah, go ahead.
How much of this was like, hey, I actually need this to, to get this up and running or to maintain this? And how much of this was like this nerdy, let's just
break
see, I don't really
things.
need to do this, but it's fun.
So you mean using K6 to find out these bottlenecks, right? That was the question.
Yes.
How much I needed to
Two
use.
things.
The
One,
structure
like,
that you show, is that something already, or that you built to see like how can I break something or induce pressure? Am I right, Nicole?
no, so the two things. One is, did you really need to put like your media server on Kubernetes, or is it like a nerdy thing? Like, why not? And two is, did you have issues already with your network before this, or did you just think it was a cool use case?
Yeah, very, very nice questions, both of them. The first one I get asked a lot, like because you tell people, yeah, I'm running my home services. Well, depending on which people you tell them you are running home services, and that already poses some questions. But if they happen to know a bit more and you tell them, yeah, I'm running those on Kubernetes, they ask, why do you hate yourself so much? And yeah, I ask myself that very same question as well. But I want to believe. Yeah, I want to believe inside my heart that there is a reason. And the reason is that I happen to learn Kubernetes for other reasons, mostly job related. And once you know Kubernetes, or conversely, if you are very, very willing to learn Kubernetes, it really relieves some of the work that takes hosting all these things, right? Kubernetes provides very nice abstractions and workflows that allow you to treat all your services the same. So in the first months, it takes some work, but I think in the long run, I've been running this for, I think, 2 years. In the long run, it pays off. Updates all go through the same process. Services will go through the same process. It is very homogeneous. And if you host one or two applications, then it's probably not worth for you unless you want to play with Kubernetes itself. But if you host, I actually don't know how many I host, but let's say more than 10, for sure it's more than 10, then it may already be worth for you. Yeah, and that will be for the first. Did I answer your first question? Does that answer the question?
Yes, you did.
It was kind of curious that when you said like, yeah, I have these Kubernetes servers for friends and family, I'm like, I need friends like that. I mean,
yeah, do you have like 100 friends and family or something?
No, not at all. I have an LDAP for authentication. I think it has like 5
Okay,
users.
this is just
so.
nerdy stuff. Come on,
Yeah.
this you can't convence me otherwise.
You can tell he really likes this stuff.
Yeah, I really enjoy it. And
Awesome.
yeah, for the second question, like, did I suspect that this was a problem? So yes and no. In practice, no. In practice, it worked well. Whenever someone went to download something from my media server, it went okay. Nobody complained about me. But I knew it was not as good as it could be. And I have it pointed, the last point of this slide that says the prior art. I know for a fact that some friend wanted to download something and they reach like 30 megabytes, maybe bytes per second, which is okay. That's why I say, okay, this may be not a practical reason to improve this. It is plenty. But it made me curious, right? This thing behind your head, why so this should be, and for context, my uplink is gigabit, like most fiber optic nowadays, or depending when you live, but it is not super rare to have gigabit.
I'm super jealous.
Yeah. Actually, I live without it for many years, so I understand. But for context, this is like 1/3 of the theoretical network bandwidth. So it made me curious, like, okay, only 1/3. I could live with 80%, but 1/3. So this gave me the excuse, right? Okay, let's dig into this and learn things.
So what
Cool.
are we looking at here?
Yeah, so as I was saying, this is more or less a high-level diagram of how this looks. There's this cloud on the top called the internet. This is where, everybody else that is not in this house physically reaches this infrastructure. And then it goes through a router and a switch. This will be your typical ISP router, the thingy that they put on top of your TV, furniture, or whatever. So that will be it. And then we have like a bunch of nodes, right? And this is a neat thing about Kubernetes. You don't need to have only one server. It is built in a way that encourages you to have many. And I think this is great because as I will talk about this later, many of these nodes are actually very small, thin machines that are like, I don't know, think computers. They will have think about Raspberry Pis. They are not Raspberry Pis, but they have a similar compute power as Raspberry Pis. And as you can have many of them, this means that you can, for cheap, get an aggregate compute power that is good enough. So I have several of these, and these run the services. An example of service will be this light green box at the bottom. I call memserve. This is not a real service. It is an application, a very dumb application built for testing, but it will be one service. And this service is accessed through Nginx. Nginx is a very old web server. I think many people that have tinkered with self-costing will know about it. And you can also run it inside Kubernetes as what we call an ingress controller. But an ingress controller is just a fancy name for an HTTP server, so don't think too much about it. And then we have like this CNI proxy. This will be a very interesting topic, but just to brief it will be like the networking component of Kubernetes. We will delve into this later. So this is more what we have. This is more or less what we have in the picture.
So this was super interesting to me when I saw this in your presentation, because it's already daunting to test networking in general, but like to add Kubernetes as a layer on top of that just adds another level of complexity, because it has its own load balancer, for example. Do you think that there are things that make it even more complicated than that?
So definitely, like it depends on how deep you want to go for network testing. But if you want to make simple bandwidth testing, there are tools that you can use for that, and as a command line, and more or less will give you a reasonable estimate. I think this complexity that you mentioned is precisely what I wanted to test here, right? Because it is like, the network gives you this. You go to speedtest.net and it tells you, okay, you have 800 megabits upload, and okay, I have 800 megabits upload. But this doesn't tell the whole story, right? What you really want to know, or what I think is super interesting, is, okay, all these moving pieces I have here, like many nodes and proxies and load balancers, are these hurting my network? Are these helping? Are these introducing problems? So this was kind of what I wanted to figure out. Not only the network itself, but the whole stack of things that is here.
It's interesting because it's a lot of complexity that you can have, and it reminds me probably not the best analogy from the virtual machine days, when we had multiple virtual machines inside a single box, each one with their own virtual IPs communicating among each other. And I remember that adding, let's say, multiple files being transferred in between virtual machines. The difference between just zipping them and single file, very big, or multiple files start and end, and you're already laughing for been there?
Yeah, no, because it is like a very common problem, right? One thing is the network bandwidth. That is what we call, okay, how many bytes can this push? And a different thing is network throughput, which typically averages more things. And this thing that you were mentioned of one file versus many files is that what we commonly refer as the overhead of each connection, right? So sending one file is just not pushing the bytes into the wire. You need to do some things like, hey, I'm going to send you a file. The file is like this. Okay, send me the file. And this takes time. So this is one of the things that just testing the network, say the width of the wire, the bandwidth, doesn't tell you. You want to do like more advanced testing. And I think that K6 was really great for this.
Oh God, they're just at the first slide. We're already asking so many questions. Please go on, Ro.
Okay, let's. But you see, this diagram will appear sliced up later. So I'm hoping that we can remember this knowledge.
We will get there.
We got from
Okay,
these questions.
okay.
So again, talking of the same diagram, and I went over this already, I think, a bit, but I will go into more detail here. There are multiple layers of indirection, and I said indirection here, one could say load balancing, I guess, but the first is not exactly load balancing. So let's say indirection. And let's see that we have, as I mentioned, multiple instances or replicas of a service. In this case, I'm using this memserv, which is like this dummy service I mentioned. So when you ask memserv for something, which instance, which replica is going to answer, right? That is a question that to answer that, we need to go through we need to understand what we are deploying and what is the multiple layers in play here. So the first layer that I will say is the most the simplest and the most basic is the ARP. You can see in this diagram that between the internet and the switch there is this virtual IP. I hope you can see my cursor. I think you can. There is
Yes,
this virtual
we can.
IP thing. So virtual IP is kind of an overloaded concept. Like all IPs are virtual. They don't exist in physical matter. But we typically say, okay, it is a virtual IP in a sense that no fixed machine has this IP. It's like floating, ethereal, virtual in the air. And what will happen is that these multiple nodes that we have will take turns to assign themselves that IP. So let's say that for right now, it could be the node on the leftmost node will have this IP. So whenever you ping this IP, you connect to this IP, you will reach this node and only this node. And then after, I don't know, 15 minutes or whatever, we're talking minutes here, so large spans of time, another node will take over and say, no, this IP is now mine. So this allows to distribute over time, and this also allows for failover. So if the node that is holding this IP goes down, another one can take over. So this is like the first layer, and this is called typically called metal load balancing, and this is powered by a thing that it is called metal LB on my cluster. So this is the first thing, right? Whenever we say to memserv hello, the first thing that is going to happen is that one of these nodes will answer for this and say, hey, connect to here. Here is memserv. So then we go into the next layer, and the next layer is the CNI and or proxy. It is slashed because it may depend on what you have on your Kubernetes cluster. This may be your CNI or maybe kube proxy, which if you have toyed with Kubernetes, kube proxy will probably sound like something you have seen. And the kube proxy or the CNI, their job is to make sure is to route a particular connection to the replicas of the service behind. So in this case, the service behind is not memserv, it's nginx. So whenever I connect, we remember to first go to a node, and then the CNI will assign one nginx replica at random and will forward this packet to nginx. This is number 2. And finally, number 3, nginx itself, it's also a layer of indirection. So nginx knows there are many replicas of memserv, and it will pick one at random and push the package to there. So I hope this was not very overwhelming. Just make sure there are these 3 layers, and we are thinking, the computer is thinking in every of these layers, right? So every of these layers can be a bottleneck, every of these layers can be a problem. And
now, Silly
Yeah,
question
go ahead.
from my end. Is this like a common layer distribution when you work with these elements, or you are just making it for a specific reason?
I think this is pretty common. So the first layer, the virtual IP layer, will only be present if you are doing so-called bare metal Kubernetes or non-cloud. I prefer to say non-cloud Kubernetes. Otherwise, this is already happening, but AWS, GCP, or whatever your cloud provider is will do this for you. The other things, yes, you have those. You typically have Nginx or another ingress with multiple replicas, and you also have multiple replicas of your service, and they are balanced 2 times. The reason one may ask, okay, why not connect to memserv directly? Why do I need Nginx in there? I already have a proxy. Typically, you offload to Nginx some boring things like TLS termination, so HTTPS, certificates, all this that, maybe some rate limiting, I don't know. It is a common pattern to do it like this.
Okay, got it.
Cool. So let's move on. I don't want to talk through this. I will only stay 10 seconds on this. This is a very snippet of code. This is the totality, the full amount of code that is inside memserv, and it basically sends you rubbish. 10 megabytes of very random cryptographically secure rubbish, and it does this very fast. This is like all that needs to be known. And we do this because we want to test the infrastructure. We don't want to test memserv. Memserv is just like a dummy application that I wrote to be as fast as possible. So to make sure this is not the bottleneck. So yeah, that being said, let's move on. So this will be like my very first test. You may notice this is very similar to the first diagram, but for the sake of testing, I am for now leaving out, the router, and I'm doing this in the local network. So we have Berta here. I love her, by the way.
Yay!
She's so cute. We have Berta here, which is doing the tests, and it's connecting through the switch. It's using the virtual IP as well, and is going to make this traffic. So as I said, this is going to be TLS traffic that enters, hops around, picks one of the nodes, this ARP, the virtual IP taking turns we talk about. Then the CNI will pick an Nginx replica at random. It will say, you take this. Nginx will undo TLS, so it will, actually perform TLS termination is the technical name. And then it will connect to memserv, which is this very dummy application we saw earlier. So I run Berta here to check, okay, how is this performing? And it wasn't very good. We got like 12 megabytes per second and an average request time of 20 something seconds per request. This was not very good. I was doing here like a fair amount of parallel requests, 30 requests in parallel, but this was like definitely not what I was expecting. And if we see here, we are taking 12 megabytes, which is not the 100 megabytes that we are promised. So sharp-eyed network aficionados here may spot this 12 number as something suspicious. If you're doing networking, 12 or 12 point something is a number that comes up quite a lot. When I did this, though, I haven't had my afternoon coffee. I'm not sure, but I didn't notice this. So if you see these slides and you see, okay, I know what is happening here, then congratulations, you are smarter than me. I thought, okay, this is TLS. TLS is messing things up. TLS is taking too much time to encrypt in traffic and whatnot. So let's get rid of TLS. And this is what I did, right? I basically, the diagram is the same because this is just a config change. I just told Nginx, okay, don't do TLS. Do the same thing you were doing, just no TLS, no HTTPS. Same thing, everything is plain text. And it wasn't great either. You could say worse, but I think this is like within standard deviation. It's just the same number, 12. This was not great either. So at this point, I said, okay, Nginx. I was expecting more of you, Nginx. You are shit. So I got rid of Nginx and
Bad Nginx. Malo.
Yeah, damn Nginx. You are playing full games on me. So I got rid of Nginx and I just said, okay, I'm going to give, instead of using the Nginx IP, the virtual IP we talked about earlier was Nginx IP. I just set an IP for a particular node. In this case, I'm calling here node A, and I told them, and I opened the port and connected directly to the memserv replicas. And now my hopes were really, really up. Like, okay, this is it. Nginx was the root of all evil, and it will work great. It didn't. It didn't work great. It was still shitty. We still have the same number, the same damn number 12. Okay, this is haunting me already, right? And if we in retrospect, I should have noticed this earlier, both because of the name and also because of this, right? I didn't have a picture, but you can see this is like a dramatic reenactment. I look, for some reason, I don't know, it was to divert my gaze in the direction. I look at the switch and I saw that the lights were orange. Oh my God, that was a nice effect. Thank you. So yeah, this was not what was supposed to happen, and we can go back to this number 12 when if you have a modern switch, and different switches use different things, but this particular model, when the lights are orange, means it has not been able to negotiate a full gigabit speed. It has only been able to negotiate fast Ethernet or 100 megabits. 100 megabits, if you like translate that into bytes, you get 12 point something. So that is why people who is familiar with networking will be familiar with that number, because it used to be the bottleneck in the fast Ethernet days before gigabit was a thing. So yeah, this was like a long story. This took a whole afternoon to fix. A connection was bad. It was a physical connection went bad. Without touching it, this happens. Do not trust network cables. They age and they age bad, and they will bite you in the booty when you less expect it. That's right. So yeah, I fixed that, and I went back to the beginning. Now my link speed was great, and I fired up the TLS ingress, and this time I was getting a more reasonable number, right? This was 50 megabytes, so half the gigabit speed. You can see the average latency improved a lot. So this was okay. I went through the full stack again just to make sure. Okay, how does this look? Did we find another bottleneck? I removed TLS. We got the same number basically. And then I removed Nginx again. And then I saw, okay, this is great. I'm at 98 megabytes per second. This is fantastic. Cool. But it was not right. Something, if you can see here,
didn't feel well, right?
Yeah, it didn't feel well. We did get 98 megabytes per second on average on the total aggregation, and the average request duration was 3 seconds, which is nice. But K6 is nice enough. It will tell you, it will tell us some more stats about the connections, and some of those connections were taking as long as 1 minute. So that is weird, right? And just for context, all the memserv replicas are running on same identical hardware. There was no more powerful nodes for this scenario. So why were some requests taking 1 minute and others like median we can see here 1 second? This does not make a lot of sense. So I decided to delve a bit deeper and try to troubleshoot again. What is this weirdness? Just to let's see if we can understand what is going on here.
Could you go back 2 slides? I just wanted to have a look.
Yeah.
For the test.
Yeah.
Okay, I was looking actually at because I saw that you have 200 requests and 96% of them passed. So I wanted to see the expected response true line, because there actually is quite a difference. The ones that passed was what the average is 1 second, and if you lump them all together, it's 3 seconds. But the timeout is still pretty high, 46 seconds. Oh, that's interesting.
Yeah.
Why were they failing?
It was very weird. So they were failing because they were timing out.
Building the case to give us the Soren case solving detective work.
Absolutely. Yeah,
I've got a hunch, but I want to see how this story delves.
I was just interested because even the ones where they passed seems like the maximum was quite high, so quite a high standard deviation.
Exactly. The distribution was very weird, and we got most of the requests were okay, and some of them were taking a lot, and some of them even were timing out. So this is why they were failing. This 38 out of 1,000 something were timeouts. And this is why I say strange timeout in the logs. They are not pictured here, but the K6 logs were telling me timeout, timeout, timeout.
I think I was already seeing some clues in your graphs earlier.
Oh, let's see. Let's see. We can later. I will ask you if you suspected what was going on. So I went a bit deeper here, and I went for the logs of memserv. Memserv was the application button down the stack, and memserv was simply logging each time it handled a request. It basically said, "Hey, I handled a request." So I did a very quick scoop through the log. So I went to one replica of memserv, which we can see here on the left, and we see that this is the span of 5 seconds, and we can see I actually didn't count them, but there are maybe 50 requests here. So 50 requests in 5 seconds, it is quite good. And on the right, we have a screenshot of the logs of another memserv replica running on identical hardware, and we can see that this is not 5 seconds. This is 1 whole minute. And in the 1 whole minute, we managed to serve, I don't know, maybe there are 20 requests here or 25. So it is quite a difference, right? Like you don't need to do the math. Just see that there are more requests in 1 order of magnitude less of a time. So something weird was going on. Some of the replicas were not handling as much requests as the others. And if we picture it back to the diagram that we have at the beginning, we see a pattern, right? We have Berta here going through the switch, going to node A through the ARP balancing, and we see a pattern. You can see by these emojis of stonks going up and stonks going down. Stonks going up seems means many requests. Stonks going down seems not many requests. And we can see this pattern where the memserv replica that was in the same node that it was using as a load balancer. Remember, in this picture, there's no Nginx. I'm attacking directly to the service. So the very same replica that shared a node with the load balancer was doing very well. And the other nodes, here there is another one, just another one in the diagram, but in practice there were a couple more. They were doing all of them terrible. So that was some kind of a hint, right? Something weird is going on. Why this asymmetry if the metal, once again, is the same? So I delve a bit, just for science, I made an experiment and say, okay, let's ensure that there isn't any replica of memserv in the load balancer. So we have those completely separate. I did that by just playing with Kubernetes the node affinity. Basically told Kubernetes, hey, ensure this doesn't happen. Kubernetes happily complied. And I could observe, as you can see by the not stonks emoji, that all of the replicas were very sad. They were getting very few requests. I don't think I have the K6 results, but they were terrible here. Oh, actually I have. There were these 55. So they were, pretty not good. And you can see here on the right, this is a screenshot of, I delved, into a node, ISSH, and I ran btop. And btop is like htop, which is like top. It's basically, okay, Linux, please tell me what is using your CPU. And you can see this at the very first row here, this ksoft IRQ. So people who have dealt with Linux for some time will know that seeing things that start with K is bad news. It's always bad news because K in the Linux world stands for kernel. So this is a kernel thing. And that is not fun to debug, and it is not fun to know what is going on.
I need to do something here. It's the kernel.
Oh, I love that. It's the kernel. Yeah, the kernel is the thing that you want to pretend it doesn't exist. It just does its job and you forget about it. And when you see it popping up, you can see that things are not, you are not up for fun. But I have a hunch here, right? I have a hunch of what could be happening. So let's delve into this for a bit. And before we delve into this for a bit, we need to talk about Kubernetes networking, which is a very fun topic, I think. I am not a huge expert on Kubernetes networking, but just by operating Kubernetes out of the cloud, you kind of get exposed into it, and you cannot help but deal with it the best way you can. And hopefully you learn a couple things along the way. I'm not sure if I have learned many things, but some, hopefully, yes. So I will try to explain how Kubernetes networking works on a very, very basic level. The very first thing that you need to understand is that pods, which are applications running in Kubernetes, they are ultimately containers, have IPs, right? They do not, applications running in Kubernetes don't typically have the IP of the machine they are running on. They have their own IP. And there is a, hey, hello. I see hello in the chat, so I say hello. There is a reason for this, right? The Kubernetes folks have a good reason for complicating things like this. And it is basically ports. So if you have two applications and both want to run on port 80, you have a problem. They wouldn't be able to share a machine because, you know, there is only one port 80 on a machine. So they basically took the big gun approach and say, okay, we're going to solve this by giving each application its own IP. And this really solves the problem you really need. Now you don't need to fight over ports. Great. But these IPs kind of exist only for Kubernetes. You know, the network where the machines are plugged in, the external network, I will call this the host network at some point, doesn't really know about these IPs. So there is you need something to take care of these IPs and to make sure that pods can communicate with each other, so that these IPs work first inside the same node. And this is what we call a network plugin, or sometimes I'm using the term as CNI. CNI stands for Container Networking Interface, and is basically the interface that plugins implement and that Kubernetes can use to networking. Basically, this CNI implementation, sometimes again called just CNI, will take care that these IPs exist and that they can talk to each other. And they typically do this not by themselves, by hand. They typically run commands in the kernel and sets up routes in the kernel. So this is like what the pod IPs are for, solve this port problem. And we have this CNI doing this hard work of making these IPs, causing these IPs to exist. Now, inside one node, let me go back for a second. Inside one node, this is all very easy, right? Or easy-ish, because inside the node, you can set up all the fake IPs you want. You don't have any kind of problem. Everything is contained. You just configure one host and okay, you're good to go. Now, what happens when you have more than one node, which Kubernetes typically has? The network on the outside doesn't know about these pod IPs. These pod IPs mean nothing to this network. This network doesn't know how to handle them, where to put these packets in. Or if we go, for example, into the diagram, for example, we see on the right there is node B with an IP 10.31, has a pod 3 with an IP, I don't know, 10.185.269. So the outside network doesn't know that this pod 3 is inside the node B. It doesn't have any clue about this. But this needs to work because pods on one node need to be able to reach pods on a different node. So how do you solve this? There are actually different ways to tackle this problem, and different CNIs tackle this problem differently, and even the same CNI can often be configured to tackle this problem differently. But the CNI plugin I was using, which is Cilium, on its default mode, use this protocol called VXLAN. And I won't enter a lot into these details, but you can imagine VXLAN as let's say, packets being encapsulated. So node A won't send a packet into the network saying, okay, please go to 10.185.269. It won't do this. It will craft a special packet addressed to the IP address of node B, 10.00.31. And inside this packet, it will be the real packet, right? This is called encapsulation or tunneling. It is a very common practice in networking. But this comes this comes with a cost, right? Doing this takes time. It is not a lot of time, but you have to do this for every packet, and you have to copy things over. And in networking, when you have to copy things, this slows things a lot. So the nodes here were doing the work of whenever an IP, whenever a packet needs to hop to a different node, they need to do the work of putting this packet inside another packet and then back extracting this packet out, right? And I believe extraction is faster, but putting the things in is actually quite a lot of work. So this turns to be a bottleneck, and this shows up kinda in this screenshot with processes either as this case of tier queue. This is the kernel doing all this work, and it is doing in this interrupt handler. So this is what was showing up here. All this encapsulation movement in and out was taking a lot of time. So before we jump into the solution, questions. This is hard. This may take a bit of time to understand. So if you have questions.
Yeah. So let me try to explain what I understood. The reason that the problem that you found was that when the traffic was hitting the service that was on the node where the load balancer also was, it was fine. There was no bottleneck. It was a lot faster. It could send more requests. But when it was going out to the other node, then there was an issue. And I think you said it was like 10 every 60 seconds it was sending versus every 5. And you're saying that the reason for that is that because of this encapsulation that has to occur on for the requests that are sent to the extra node, that little bit of CPU time for every single request was just taking too long and becoming a throughput bottleneck. And because the one that was within the same node didn't have to do that because it was already within the node, so it knew about the IP address, that wasn't happening. Is that right?
That is exactly what happened. I think you explained way better than I did.
It's a little like what I was mentioning earlier with the files, right? That that added processing in between. Because from the example that I was giving earlier, like having, I don't know, 1,000 small files, if you zip them all together, it's easier because you are not doing, and I always thought it like you have like 3 cars that have to go through your garage. You have to open the door, one car goes in, close the door. That opening and closing the door takes some time, takes processing, demands resources. But if instead of 3 cars, you have like a long bus, it just opens once, the whole bus goes through, and then it closes, you have a third of the processing because of that. And in your situation, the kernel was working through that opening and closing the door a lot more than it should, right?
Exactly. That is what happened. The kernel had to do this extra work to put these network packets outside of the node, because outside of the node there is no knowledge of how this pod network works.
Because it's like getting out to the real network and into the other pod, right? So
exactly.
If you are both virtual, why don't you just talk to each other? I think.
Exactly. Oh, this is actually a very good question. And it turns out that in some scenarios you can do that, actually. And there are some, as I said, there are different ways to solve this problem. And the one I'm going to show is probably the most naive, but it is a way. And you can over-engineer this with BGP and routing protocols that will make the external network aware of the Kubernetes network. That can be done, but this is very complex and requires like expensive hardware and a lot of complexity. I didn't want to put in. Even I, like, even a person that runs
yeah,
Kubernetes
even
at home,
you.
yeah, everybody has his own line that say, okay, I'm not going to run BGP on my home infra, and this was my personal line. So yeah, just to cut costs and complexity, let's try to keep this thing simple. So it turns out that in some scenarios, if you're lucky, there is another way you can work around this. And just before hopping into the next slide, just to use the same diagram here, the problem I was saying is that the outside network that doesn't know about the IPs from the pod network, right? But there is a trick, because layer 2 networks, and by layer 2 networks we mean every network that is directly connected through a switch. So in other words, there is not a router in the middle. Again, in other words, on the same subnet, you will sometimes hear it that way. The layer 2 network, the physical switch network, doesn't really care or know about IPs, right? It cares about Ethernet frames. It doesn't really care about IPs. So we can exploit that. We can take advantage of that. And if the network doesn't really need to care about IPs, so the network can tolerate pod IPs being pushed into there, then we only have one problem to solve, which is the nodes themselves. The nodes themselves, Linux, the outside of Kubernetes, the Linux kernel itself needs to know in which node a pod IP is. So if we manage to make the nodes aware of this, then we don't need to take care about the network, because again, the network won't care about the IPs. Only the machines that are inside this network care. So there is a way of doing this. Cilium provides a way of doing this, which is what they call disable. I think it's called direct routing. I'm speaking from the top of my head. Don't quote me on that, but there is a link here. Maybe we can post this somewhere for someone that is curious. But you can basically ask Cilium, again, my CNI plugin, very nicely to do this work for you, and say, Cilium, will you be so kind to, whenever you see there are pods appearing, telling the host this pod is on this node? And if we do that, if we convince Cilium to do that, then our problem is solved. We don't need to encapsulate our packet directed to a pod IP into another packet. We can just push the packet directed to the pod IP into the network, because other node, the receiving node will know that this is an IP address it can handle, so it will respond. And to put this to put some numbers into this, here is the output of an IP route command. This is on one of the nodes, and you can see the blue box here is like the regular IP of the node. So you can see in this case is 10.0.0.10, and you can see it is like a regular IP. It's a /24, so the net mask will be 255.255.250, and it has a gateway, which is my regular router. Nothing fancy here. Now, the green box is the interesting thing. You can see here that there are some IPs. This you may remember, and let me go back for a second. These 2 slides actually. 10.185/16. These are pod IPs, and now these are pod IPs are in the routing table of the node. So the node is now aware of these pod IPs, and not only that, it is aware that the ones that go with 0.0/24 are in the node 30. The one that's done with 185.1.0 are in node 31, 185.2 are in node 33, and so on. So Cilium was very kind to set this up for us, and now the nodes are aware of this and know that they can push pod packets or packets directed to pod IPs into the network, and they will receive them and do wizardry that the CNI does. So this is how it works. And if we rerun our test again and we hop into the node, you can see that the overall CPU usage is pretty high, because in the end, something will be the bottleneck, right? Something. So the overall usage is the same. But, excuse me, you can see that this K thing, K-soft IRQ, is way down. The usage is way down from 40%, if you remember, to 20%. So we managed to cut the work that the kernel had to do by half, at least for this particular interrupt handler. So that is great. So we hop into K6 results. We can see that now we got an amazing 100 megabytes per second, which is very close. Well, yeah, very close within deviation of the link throughput. So we did it. We managed to find the bottleneck. You may see, the keen-eyed of you may see that some of these requests are failing. Don't pay too much attention of this. This is because the test I had was a very optimistic test and was asking for, I think, a 3 seconds percentile latency. So here you see some X, but the requests were working, and they were reaching the node with full throughput.
I think it's because of this weird thing that we talked about actually internally. The HTTP rec failed with a check is like the request where the rec failed was true because it's a Boolean. So because everything's in an X, that means it didn't fail.
Exactly. Yeah, they failed to fail.
Oh man, we debated this. There were several calls.
I can guess, because this is something I asked the team, right? Like, what am I supposed to read out of this? So yeah, this were okay, and this duration with an X is the thing I was talking earlier about the percentile being the threshold I said was too optimistic, but the bandwidth was pretty okay and pretty solid.
Yeah, and the max duration now is 10 seconds, which is much more reasonable.
Yeah. So this is great. Now, if I don't have like the screenshots for the logs here, but if we had, we will see that now they are pretty much even. Maybe there is a bit of an advantage from again, the replica sharing the load balancer. There will always be, right? If you don't have to hop into a wire, there will always be an advantage. But now it was not causing timeouts. And just to finish, there was one more thing that I may want to add here. That is, maybe someone as crazy as me should be wondering: should I do this? Should I disable this tunneling? Is it worth to do it? And I will say, don't rush, because this happened to me, because these nodes are actually, as I talked in the beginning, very low-end machines. They are think Raspberry Pis. They have only 2 cores, and they are very small cores. They are thin clients that I bought secondhand for real cheap. So and I happen to test this, but it's outside of the slides. If you run beefier nodes, like with real Intel, I don't know, Ivy Bridge or above, or Haswell or above, so newer generation Intels or AMDs, the kernel will probably fast enough doing this encapsulation, and it will be faster than the network. So you may not see this if you run powerful or relatively powerful machines.
But it's something very interesting that you point out on this experiment, or finding out, just when you mentioned the Raspberry Pi. So what, like, you're kind of testing in pre-prod staging devices that are kind of smaller than what we would be used to see in production. I love when you mentioned that, because you are, by decreasing the size, simulating possible bottlenecks at greater volumes that people with better CPUs, better infrastructure will see. And this is, I think, super interesting set of experiments that you were removing a piece, running K6 again, putting it back, and going back and forth. And it's something super, like, you were doing like this round trip, and the kernel was processing that round trip, and most probably hitting them, the router or your external network. I've seen that again with some virtual machines. It reminded me a lot on an apartment building where the receptionist had to go up to an apartment and then go back and bring it to another apartment and do some of those trips. Like, dude, your apartments are next to each other. Like, as long as we know that is the table, we don't have to do that round trip and carry and process those packages all the way. And it's very interesting how, with these tools, you manage to diagnose, identify, and see, like, hey, we're kind of like doing some weird steps or extra steps not needed, and finding this configuration that just, I mean, I wouldn't say just solve it, because you will always have processing in between pods and Kubernetes components. But I think this is a great example of how can you, like, mixing up some experience understanding, some K6 with Bertha and everything, give you like a very good diagnosis. This was like I was watching a CSI episode.
We have a few comments here from Ahmed Casa. This is the best way to do router config even without Kubernetes.
I will say it depends on your network. Again, if you don't run Kubernetes, you probably don't need to care a lot about these virtual IPs because they won't exist. So your network already works like this. When you have several machines on the same subnet or same L2 network, whatever you want to say it, they are not encapsulating anything. They are talking directly to each other because they know, okay, that the whole network is directly reachable. So I don't need to do weird things. I don't need to go through the router and back.
I will argue, I have been in some situations where weird routing tables will make you some of those hops. I've been in projects where the performance is like, we're in the intranet. We are having like a lot of latency. Where is it coming from? It was just like a silly routing table that was just like someone decided that it had to come to the router talk and go back to the switch and do some weird trips, even if they were in the same network. So I do agree with Ahmed. These situations may be in physical here and there, and especially with load balancers that you just left out of the box and are not configured. I have seen also some of this, and when you were having the several seconds up to minute and all these waiting times, in your graphs as well, I started to see like it's called like stair steps, and then sudden falls, stair steps, sudden falls. You had situations with queuing theory there happening. The load balancers at times will do that as well. Physical load balancers that suddenly like, yeah, I have a lot, switch to other one, switch everything. And then you've seen those tables, those situations, right? All sorts of connections lost. And I mean, this is a very interesting exercise that brings me lots of memories from bare metal, real life, not pod life, to call it in a way. But
pods
I
are
totally
not real. They live only in our imagination.
So we have another question from Ahmed. They say, which metric on the K6 report helps us to evaluate our network health? Thank you.
So in these slides, you probably, this is way too early. Here, this is the one. In these slides, you saw me sometimes remark the data received one, the rate of data received, because this is like a very basic, even naive metric, which is okay. How many requests, how many data did we manage to bring back and forth? This is one thing, but doesn't tell you the whole story. I will say that probably the one that will tell you a nice piece of information will be the duration. So this is statistics for the duration of a request, because you will have the average and the median, which kind of tell you, okay, how everything a bit on average from the bird view works. But you also want to watch out, which Nicole very rightly pointed out. Okay, how are the minimum and the maximum? How much they differ from the average or the median? Because if they differ a lot, then you have, it is not very predictable. Some connections will take a lot, some others will complete faster, and that is often an indication of trouble, right? Something is amiss if there are huge disparity in these values. So if I could just pick one metric to give the very first look at, could be this one, the duration per request.
I would say like don't focus on a single one, because as you very well mentioned, there are some like you need to paint the whole picture to know these standard deviations. Like, is it too big? Why am I having so big? Means that suddenly I have some spikes that may mean most of the time networking issues, lost packages, things like that. It's tough to choose just one. Response time always is like our cornerstone, but for almost everything. But mix it up with a little bit else, and you have a better picture. Even the backend ones that you had for the graphs, right? The CPU, sorry.
Absolutely. I also want to point out that this is just one part of it. Like K6 has some metrics, but it's still a limited view. It's like the round trip. And if you're looking for like specific stops, like how long did this stop take, this leg between these components, K6 isn't going to be able to tell you that because it's throughout the whole thing, unless you're doing something like tracing. And that's where all these other pillars of observability come in. I don't know, Ro, if you've tried Grafana Kubernetes monitoring, because it's actually, I had an opportunity to try it recently, and it's actually pretty good. Because one of the things it does is it has a lot of these these CAN dashboards already for network on different levels, like node level and then pod level, and then logs for everything. I mean, I don't know. I think like if I had to do something like that, instead of having to go to each thing and having to fetch the logs individually, and that it sounds like that's what you also did. I might not know how to like what to look at or where, or like it's just very overwhelming. I did really like just being able to have it all set up for me. So that's also an option.
Yeah, absolutely. I think the like this dashboards help a lot, and probably this thing that I did just like logging into the machine and running top. If I can do this because I have like 5 machines here, right? But if you are operating on a bigger scale and you have 100, you are not going to logging into each one and say, okay, is this one loaded? Is this one loaded? Is this one like that wouldn't make sense? And both for small cases, but especially for larger cases, it helps to have like a dashboard that can tell you, okay, this is what is at least not what is going on, because a metric will never tell you what is going on. A metric will tell you this is what we are seeing on this particular, through this particular keyhole. And if I could have shown a dashboard for the nodes, and you will have seen the very same thing. You will have seen this node with very high CPU, and if we listed the processes, you will have seen in Grafana the very same thing. So I definitely use it, and I definitely recommend it.
Awesome. Thank you so much for joining us. We're already a little bit over time, but I feel like we could have talked a bit more. We need to have you back to maybe talk a little bit more about the changes to K6 Disruptor once you've, actually had time to work on it.
Cool.
Any last words from either of you?
Well, if I can, from this very interesting guided tour, Ro, you totally reminded me on the days that we were like, again, a performance and load test often is like a CSI. You have bullets here, there's blood over there, a testimonial here. And you have to put together everything that is happening to really figure out what is it. It's not, as Nicole very well said, it's not only the X-ray that you get from K6, you also need a stethoscope to put it here and get some other studies, blood work. I don't know, too many analogies, but that's how it goes. And it's that intense, entertaining, and interesting to figure out and solve the mystery.
Yeah, absolutely. That's what engineering is about, right? And I think it is at least a nice part. And I think having the right tools to do this is what really allows you to figure the whole story out of the details.
Awesome. Well, thank you everyone for watching, and we'll see you next week on K6 Office Hours again. And also, happy Pride Month. Look, I have my Pride
Yay.
Kubernetes shirt. All right.
Uh-oh.
Thank you,
Absolutely.
everyone. Have a good
Thank you for having me.
weekend.